All right, let's talk over pH, neutralization, and titrations. So a little review. Acids are things that add H plus to a solution. They form H3O plus, a hydronium ion. For bases, there are two types. There are bases that are ionic, and they have hydroxide in their formula, like NaOH. And there are bases that are covalent, like NH3. And what those kind of bases do is they rip a hydrogen from a water molecule off, leaving behind a hydroxide ion. So that would form NH4 plus in this example, thus also increasing the hydroxide concentration and making it more basic. So an acidic solution is when the hydrogen, hydronium, you can say it either way, when that concentration is higher than the hydroxide ion concentration. A basic solution is when the hydroxide ion solution is higher than the hydrogen ion concentration. A neutral solution is when the concentration of the hydrogen/hydronium and hydroxide ions is the same. And I like to tell the story of the professor who, this wasn't a professor of mine, but someone told me that they had this awesome professor who had 6 molar HCl, and he like dipped a pH paper strip into it in front of the whole class. It turned red. So he was proving like, yep, this is really an acid. And then he took 6 molar NaOH, extremely basic, put another pH strip in. That one turned blue. And if you drank either of these, you would die. But the professor mixed them together in one big glass, and then he just drank it in front of the class. And that's because when you add these two things together in water, the Na and the Cl split into ions, and then H is with the OH, so that's the same thing as H2O. So again, this OH goes with this H, and the Na is with the Cl, only that dissociates, and so all he drank was salt water. So this is neutral. So pretty impressive that that is what happens when you combine these two things. pH measures the concentration of the hydrogen hydronium ions. And a pH scale goes from 0 to 14, and it tells you how acidic or how basic something is. So it's increasing in strength as it gets closer to 0, as well as 14. Just depends on if you're talking about a stronger acid or a stronger base. So what exactly is the difference? Like, why is a strong acid so strong? And it kind of is counterintuitive because a strong acid or base actually splits up in water. So all of the molecules dissociate. So like, look at this picture of the strong acid. See, it's represented by this red and white sphere. And once they're in solution, look, they're all separated from each other. But the weak acid, only some are separated. Lots are still together. Same for a base. Here's a strong base. Notice in solution, all of the NAs and the OHs are broken apart. But in a weak base, maybe only one breaks apart. So not as many hydroxide ions in solution. So weak acid or base, only some of the molecules actually dissociate. Okay, so let's learn a little bit more about pH. As you know, pH is related to the concentration of the hydrogen ions. The concentration is represented by these little brackets around an H plus. So the concentration of hydroxide is similar, only it's brackets around the OH minus. If the concentration of a hydrogen ion solution is 0.1, what that means is it's 0.1 moles per liter. And you also might see it written in scientific notation sometimes, 1 times 10 to the minus 1. So let's study this table and see if we can figure out how these relationships work. So when the pH is 0, in scientific notation, it's 1 times 10 to the 0. That's what the concentration is. When the pH is 1, it's 1 times 10 to the minus 1. When it's 3, it's 1 times 10 to the minus 3. When it's 6, it's 1 times 10 to the minus 6. Okay, I see the pattern, and hopefully you do too. As far as putting it in decimal form, well, it's always the number of zeros after the decimal plus 1. That's the pH. So for example, here there's 1, 2 zeros, and the pH is 3. Here there's 1, 2, 3, 4, 5 zeros, and the pH is 6. Here there's 1, 2, 3, 4, 5, 6 zeros, and the pH is 7. And so on and so forth. So if you know the concentration of a solution in decimal form, how can you figure out its pH? It's the number of zeros. I was like, that looks wrong. It's the number of zeros after the decimal plus 1. Prove it. What is the pH if the concentration is 0.01? The pH would be 2 because it's 1, 0, and then we add 1. So 1 plus 1 is 2. What if we know the concentration in scientific notation? What's the pH? So pH is equal to the negative exponent. So, or the positive of it. I'm not sure how to say it, but like, for example, if it's 1 times 10 to the minus 3, the pH isn't minus 3, it's just 3. So prove it. What's the pH if the concentration is 1 times 10 to the minus 9? The pH would be 9. As pH goes up, what happens to the concentration of hydrogen ions? It goes down. And we can check the chart. So as the pH goes from 1 to 3, the concentration went down. It got weaker. It went from 0.1 to 0.001. Then it's going to ask us the opposite. As pH goes down, what's happening to the concentration of hydrogen ions? It goes up. Okay, solution A has a pH of 5, solution B has a pH of 9. What is the hydrogen ion concentration of each? Well, it's 1 times 10 to the minus 5th, or 0.00001 for the pH of 5. And for the pH of 9, it's 1 times 10 to the minus 9th, which is the same as 0.000000001. Identify the solutions as acidic or basic. Well, pH of 5 is less than 7, so that's acidic. pH of 9 is greater than 7, so this would be basic. Which solution has a higher concentration of hydrogen ions? The pH of 5. Look, it's 0.00001. That's much higher than 0.000000001. How many times bigger? Well, let's do it. 0.00001 divided by 0.000000001. How many times bigger? I'm going to put this into my calculator to make sure I get it right. Oh, it says error. Okay. 0.00001 divided by 0.0000000001. 10,000. So that's a big difference, 10,000 times more concentrated. So when a pH shifts by 1, it's not really changing by just a factor of 1, it's changing by a factor of 10,000. Or yeah, actually this was, it's changing by a factor of 10, sorry, because this was 4 units, changing from 5 to 9. Another cheat way someone taught me is you can just do, okay, pH of 9 minus pH of 5, that's 4. That's how many zeros. So 10,000. Okay, let's talk about neutralization reactions. This is a reaction in which an acid and a base produce a salt and water. Okay, we've already seen an example of this. Okay, so the first two things like swap places. So now the Na is with the Cl and the H is with the OH. So let's do some more examples. So H3PO4 plus CaOH2. We know it's going to make water, so don't even think. Just write out water. And then we also know what's left over is Ca and PO4. But we've got to check charges. Calcium's a +2, phosphate's a -3. So this is going to be Ca3PO4 I'll put a little chart off to the side too. I realized I haven't done that yet. All right, now we've got to balance it. So Ca3, let's put a 3 in front of the Ca. PO4 2, let's put a 2 in front of the PO4s. That's 2 times 3, 6 hydrogen, plus another 3 times 2, another 6 hydrogen. That's 12 hydrogen, so you need a 6. Now we're balanced. Okay, let's do another one. Another acid plus another base. We know this is an acid because it starts with an H. We know this is a base because it ends with an OH. So we know it makes water. What else does it make? Potassium's got a +1 and sulfate has a -2. So this makes K2SO4. So to balance, we need a 2 and a 2. All right, titration is the process of adding a known amount of solution of known concentration to determine the concentration of another solution. And the equivalence point is when the number of moles of hydrogen, hydronium, those can be used interchangeably, ions equals the number of moles of hydroxide ions. So it's like they all cancel each other out. In other words, when you have the same mole to mole ratio of reactants in the balanced chemical equation. So let's look at an example of that. How many moles of HCl does it take to neutralize 6 moles of NaOH? Okay, well, HCl has 1 H per molecule and NaOH has 1 OH per molecule. So if you've got 6 moles of OHs, how many moles of H's do you need to cancel out? And the answer would be 6, because it's a 1-to-1 ratio. Okay, so let's do that again. How many moles of HCl would it take to neutralize 6 moles of NaOH? Is this the exact same problem? I meant to do something different. So let's do, would it take to neutralize 3 moles of NaOH? Okay, so you've got 3 moles of NaOH. You're going to need 3 moles of hydrogen ions. 3 moles of HCl to neutralize. Okay, here's a little bit of a trickier one. How many moles of NaOH do you need to neutralize 2 moles of H2SO4? Well, for 1 mole of H2SO4, you need 2 moles of NaOH. So if you've got 2 moles of H2SO4, you're going to need 4 moles of NaOH. And this makes sense because 2 moles of H2, that's actually 4 H's. So you're going to need 4 OH minuses because the NaOH only has 1 per molecule. So you need that many to neutralize. And then here's a weird one. What if you get a weird number? How many moles of H2SO4 do you need to neutralize 2.4 moles of NaOH? Well, again, for every 2 moles of NaOH, you would only need half as many moles of H2SO4. So it would be 1.2 moles of H2SO4 to neutralize that base, because it's sort of like the acid is twice as powerful. The end point in a titration is when the indicator changes color. It's a little bit past the neutralization point, a little bit past the equivalence point, because it takes a little extra hydroxide to change the color from its neutral clear to, or acidic clear to that light pink. Okay, steps for doing a titration. Start by writing a balanced neutralization equation. Then write all your information underneath the equation. Determine moles of your known acid or base by taking molarity times liters to get moles. Use the mole-to-mole ratio to determine the moles of your unknown base or acid. Final step is to determine the concentration of your unknown. Okay, so let's do a problem. A 60 milliliter solution of HCl is completely neutralized by 30 milliliters of a 0.2 molar NaOH. What's the concentration of the HCl? Write the reaction first. HCl plus NaOH makes H2O plus NaCl. All right, let's write our information down below. I'm going to divide the milliliters by 1,000 to get these into liters, just to make it a little bit easier to work with here. So we've got 0.2 molar NaOH, and we needed to add 0.03 liters to neutralize the 60 milliliters of this mystery acid. So first step, do our molarity times our liters to get how many moles of NaOH we had to add. We had to add 0.006 moles of NaOH. Now, for every 1 mole of NaOH, it's neutralizing 1 mole of HCl. So that means there were 0.006 moles of HCl that we neutralized, divided by 0.06 liters. That is a 0.1 molar solution of HCl. Makes sense because it must not be as strong as the base, because we needed to not add very much of this stronger concentrated base to double the amount of the acid. And then let's actually watch this titration happening here. So I'm going to click on this video. Hopefully it records us watching the video. There we go. Great, nice add. Okay, so what they're talking about here is this is a zoomed in version of what's in this flask. So here's our 60 milliliters of HCl. And as you can see, the H's and the Cl's are in here. And then slowly, I'm going to pause it for a second, you're adding this 0.2 molar NaOH. So they're adding it kind of in increments, like 5 milliliters at a time. So watch what happens. So as they added some NaOH, the H's, the little blue ones, are getting with these new OH's that are being added. And we're also seeing some NAs being added too. They're kind of just showing them appearing here. They're still, at this point, if we pause for a second, the pH, it's still acidic because there's still loose hydrogen ions, these blue ones. The green ones are not a factor because they're neutral. These beige ones are not a factor because those are neutral as well. And then water molecules, are, of course, are neutral. So that's why the pH is still low. All right, let's keep going. So then you keep adding more and more and more. Still acidic. Okay, adding more NaOHs. Boom. Look, we're at a pH of 7 because all of the H's have combined with the OH's. And that was after we added a total of 30 milliliters. So this is the equivalence point. And then as you add a little bit more, now you made it basic because there's extra OH minuses in the solution. And so now the pH is much higher than 7. And this would all turn pink. I wish they would have turned it pink in here so that you could see that that little extra hydroxide changes the indicator. But that is an overview of titrations. If you haven't done it yet, it actually becomes a lot easier to understand when you do it. So, yay.